Morning, everybody. So today we're going to continue on talking about electrophilic aromatic substitution reactions. Before we do that, I want to review real quickly the rules of aromaticity. What are they? Molecule has to be cyclic. Complete conjugation. Planar. And what? Which is? That's right. So all of those things have to be satisfied in order for us to have an aromatic system, right? What does aromaticity mean again? Unusually stable, right? Now that's really what it means for us, right? Doesn't mean that it smells good. A lot of aromatic things actually stink, okay? But they can undergo chemistry even though that they are unusually stable. And that chemistry that we need to talk about and continue to talk about is electrophilic aromatic substitution, which we've already talked about the general electrophilic aromatic substitution reaction mechanism a little bit, but we'll review that again today. And so we'll talk a little bit about electrophilic halogenation, nitration, sulfonation. We'll start talking a little bit about some Friedel-Crafts chemistry, which allows us to make carbon-carbon bonds with an aromatic ring. So we've already talked about this a little bit. We won't spend too much time, right? We can actually substitute an electrophile for a hydrogen and make new bonds to aromatic rings. Noticing that both the starting material and the product have an aromatic ring, this is allowed. Typically, aromatic rings do not undergo these normal addition reactions that we would normally think of for an alkene, meaning that these double bonds that are drawn in benzene are actually a little bit misleading, right? They're really not double bonds that are sitting there all by themselves like you might think as it's drawn, right? This is actually a delocalized system. It's aromatic. It has some special properties, okay? We talked a little bit about the general reactions that we can do, right? We can replace a hydrogen for a halogen, right? Chlorine and bromine. What is absent up there? Iodine. It's very hard to put an iodine on an aromatic ring, and it's very difficult to put a fluorine on an aromatic ring. But we can put chlorine and bromine on quite easily if we have a catalyst. In this case, iron trichloride or iron tribromide work really well. The electrophile, and again, we should put these in air quotes, are chlorine plus and bromine plus. Although we don't really have a solution of chlorine and bromine plus, we'll talk about the mechanism of this today. We can do nitration, replacing the hydrogen with a nitro group using a mixture of nitric and sulfuric acids. We can make sulfonic acids by using a mixture of SO3 and H2SO4. We can make carbon-carbon bonds if through Friedel-Crafts chemistry using alkyl halides. Typically, most people use alkyl chlorides for this, although you can use alkyl bromides or alkyl iodides, but nonetheless an alkyl halide. Aluminum trichloride as the catalyst, and it allows us to make carbon-carbon bonds, alkyl benzenes. And then, of course, we can make carbonyl-containing compounds by using, what's that functional group? RCOCl? Yeah, acid chloride. So if we take an acid chloride, aluminum trichloride, we can make ketones, for example. Okay, and these are great reactions for making carbon-carbon bonds. Okay? So we talked about the general electrophilic aromatic substitution reaction where we take a benzene ring and an electrophile. Now, how do I push the arrows? I move from the pi system to what? I couldn't hear you. Okay. And we get a is that just any old carbocation? It's kind of a allylic. It's actually more conjugated than an allylic carbocation, so it's really a fairly stable carbocation. But is it aromatic? So what happens? We lose the hydrogen, right? So E plus always has to have some kind of counterion. That counterion comes in, removes the hydrogen, we reform, so we get, of course, an acid, and we get the generation of our carbon electrophile bond. Okay? Easiest mechanism that there is for you to really understand, just a few steps, right? Not too complicated in the arrow pushing. What's complicated is how you get the electrophile. Anytime you can generate an electrophile, you have the potential of doing electrophilic aromatic substitution. Not all electrophiles will do this, but anytime you see an electrophile in an aromatic ring, it should be something that you're starting to think about. Maybe we could do electrophilic aromatic substitution. Okay? So now in the halogenation reaction, we can take an aromatic ring. Of course, we're always picking on benzene in these lectures. And if we take chlorine, what's the physical state of chlorine at standard temperature and pressure? It's a gas, right? So we take a solution of benzene, we throw in some iron trichloride, and we bubble through chlorine gas. It's not a fun reaction to do. Chlorine gas is quite toxic, and you end up making chlorobenzene. Can be done. You can also take an aromatic ring, a solution of an aromatic system. You can take iron tribromide and place in there, and then you can drip in bromine. What's the physical state of bromine at standard temperature and pressure? It's a liquid. It's a volatile liquid, but it's a liquid. It's a lot easier to handle. And so in the laboratory, when we're working, we almost never do electrophilic aromatic substitution using chlorine, because we have to have regulators that are rated for corrosive gases like chlorine, and you have to have special tubing, and you have to have a hood that's rated for it, and all this kind of crap. Bromine's pretty easy. I just have to get a pipette out what I need.
Does it matter what mole equivalent you use of this stuff?
Of mole equivalent of what?
Like the chlorine and the bromine?
Typically we use an excess, but it has to be 1-to-1 at least. So for every mole of aromatic system you have to have at least 1 mole of chlorine. But quite frequently we'll use it in slight excess. Bromine is a lot easier to control the stoichiometry. Chlorine's very much more difficult because it's a gas. It's hard to control how much of the gas you have. It can be done, but it's more expensive. You can use iron trichloride for the chlorination. You can use iron tribromide for the bromination, or you can simply go get some iron filings and put in the solution. So I can take my benzene, I can put just regular old iron in there, and as I start to add the bromine, what would happen? It forms the iron tribromide, what we call in situ. It generates it in the flask, okay? And it's a lot cheaper to buy iron filings than it is to go buy iron tribromide, even though iron tribromide is not that expensive. A lot of people will just use iron, and it generates the catalyst, as we say, in situ. Okay? So, now let's think about the mechanism of this. So, let's say Keyshawn has bromine. I'm going to draw it out here a little bit. And iron tribromide. How do we generate the electrophile? What's the mechanism for generating the electrophile here? How do I get to a Br+? The bond? So if we do what? So if I go from here to here and generate, won't work. There's a partial positive charge on the iron. That is true. So what is iron here? A Lewis acid or a Lewis base? It's a Lewis acid. Iron tribromide is a Lewis acid. What's bromine? Why? What have I not drawn that it has? It's got lone pairs all around it, right? So if we look at that, I've got a Lewis base and I've got a Lewis acid. So what happens? What do Lewis acids and Lewis bases do? They react. How do they react? How would I make that reaction? How would I draw that? Where do we start the arrow from? We start from the lone pair of the Lewis base, right? And where does it go? But we don't have a positively charged, but we do have a Lewis acid. Not all Lewis acids have to be positively charged. They just have to be able to accept a pair of electrons, right? The definition of Lewis acid is not that it's positively charged. The definition is that it's an electron pair acceptor, right? Just so happens a lot of them happen to be positively charged, right? So what happens? I draw the arrow from here to here, and I make what's called a Lewis acid Lewis base complex. Now, in doing that, where are my formal charges? If iron was neutral and I donated a pair of electrons to it, what does its charge become? It becomes minus, right? It's picking up electrons. What happens to the bromine that's donating the pair of electrons? Becomes positive, right? So overall, it's neutral, but we do have atoms with their formal charges, right? Do I have Br plus now? I do have Br plus, right? I have a positively charged bromine. So now, the aromatic ring, oops, not E, H, comes in and reacts with it. Which bromine gets attacked? I don't have a negatively charged one. It's one of the neutral ones. Which neutral one is it? That's why I said Br plus in air quotes. It's not really the Br plus that's doing the chemistry. It's this bromine. That's a good leaving group. That's a positively charged bromine. It's going to be a good leaving group. It's going to take that pair of electrons with it. And so we form this plus what? What do we get? What's the counter ion? You got a positive charge, you have to have a counter ion. What's the counter ion? Come on, I know it's Monday. Say it. Yep. Fe, I'm going to, whoops, Fe minus. I'm going to draw that one bromine out. Now I told you that iron tribromide's a catalyst, right? What does that mean? Speeds up the reaction and it's not used. Did I just use it?
Nope.
You sure?
You use iron 4 bromide.
Well, okay, iron tetrabromide. But where did it come from? From the iron tribromide, right? So technically I've used my catalyst. But I know that that is not the definition of a catalyst, so what has to happen? I have to regenerate it somehow, right? How do I regenerate it? I regenerate it by losing a bromide. And it turns out that this bromine can leave as bromide, give me my product, plus HBr plus FeBr3. I've just regenerated my catalyst. None of this stuff is the tough part. Knowing how to generate the electrophile is the tough part, right? If I add bromine to benzene, nothing happens. I add a little iron and make iron tribromide. Now all of a sudden the chemistry occurs because I make the bromine more electrophilic, right? If you think about it, why would bromine itself want to be an electrophile? It's got electrons around it. It's got an octet. Well, we need to react it with a Lewis acid and make it more positive, if you will. But it's not the positively charged bromine that actually functions as the positively charged bromine. Can anybody tell me why that is? Why doesn't the aromatic ring just attack that bromine. There's hindrance. The one on the end is the easiest one to get to. That positively charged bromine is pulling electrons to itself, which makes this bromine electrophilic. Makes it partially positive, right? This type of chemistry is actually quite useful in a variety of generating a variety of products that are useful for us, some of them that aren't so useful. So for example, here is the molecule with an aromatic ring and a chlorine on it. That has to be put on using electrophilic aromatic substitution. This is Wellbutrin. It's also known as Zyban, which is a pretty potent antidepressant. It's a very simple molecule. What other functional groups are there? We've got an aromatic ring with a halogen. What else do we have? We have a ketone. What else do we have? We have an amine. What kind of amine do we have? We have a secondary amine. Do we have any chiral centers? We do. We have one chiral center, right? And so this is Wellbutrin. It's a highly prescribed antidepressant. It's a bit older than Zoloft by quite a bit, I believe. Zoloft has since surpassed it in sales. Here's an antihistamine, chlorpheniramine. Again, we have some aromatic rings. This benzene ring has a chlorine attached to it. We also have a pyridine ring, another aromatic ring that is just substituted by this carbon, right? And then, of course, we have another tertiary amine up there at the top. And then this interesting concoction, these dichlorophenoxyacetic acids. These are pretty simple molecules to make. You'll notice that it is actually a mixture of both a dichloro acid and a trichloroacid. It's because it's difficult to stop at the di, and so they make this as a mixture. This is a very potent herbicide that was actually used in Vietnam as a exfoliant. So when you're fighting an enemy in jungle warfare in the jungle, or guerrilla warfare, I should say, in the jungle, leaves get in the way, right? And so what they would do is literally take these large tanker airplanes full of Agent Orange over battlefield areas and spray it liberally with this material and exfoliate the jungle so that you could see the enemy better. Turns out, many of you might know that there are a number of our Vietnam vets who are suffering from the consequences of being sprayed with Agent Orange or working in a field contaminated with Agent Orange. So there's beliefs that it's caused cancer, mental issues from excessive exposure to these types of compounds. But it is a very potent herbicide, and I don't believe it is utilized anywhere in the world any longer, though. I could be wrong about that, but it's certainly not used by the United States anymore. Nitration and sulfonation allows us to make carbon-nitrogen bonds in the nitration reaction, and in the sulfonation reaction we can make carbon-sulfur bonds, These nitro groups, of course, we can actually reduce them onto amines, and we'll talk about that later when we get into the amines chapter. So making these nitro compounds is actually quite useful. You really just need a mixture of nitric and sulfuric acids. You all are going to do an electrophilic aromatic nitration in lab. You will use a mixture of nitric and sulfuric acids. It's a very easy reaction to do. You just basically mix everything up. You typically have to do this at low temperature on ice because it does tend to get quite hot when you mix these acids together. The yields for these types of reactions are usually quite good. Sulfonation's a little more complicated from a practical standpoint because SO3 is a gas. Again, gases are always kind of problematic. But you can buy a solution of sulfuric acid with SO3, and it's called fuming sulfuric acid. You can buy it and you can just measure it out, but you still have to work in a fume hood because it's saturated with the gas, and so once you open the bottle, the gas starts building out of the bottle, and it's kind of nasty. But nonetheless, you can buy solutions of SO3 and H2SO4 and use it pretty easily. Interestingly enough, how we generate the electrophile in the electrophilic aromatic nitration reaction is pretty interesting. So if you look at it, we've got a mixture of nitric acid and sulfuric acid, and it's going through this mechanism. Can you tell me what's weird about that? An acid reacting with an acid, which means that one of the acids must be acting as a base, right? And so if you look at it, which one of those acids is acting as the acid and which one is acting as the base? Which one of these acids is the base? The nitric acid. This oxygen atom on nitric acid is a base. How would you know that if you were to look this up in a pKa table? Which acid would have the lower pKa? The sulfuric acid would have the lower pKa, right? It's the stronger acid. And so when we add the nitric acid to it, you protonate that oxygen with the sulfuric acid, right? And you end up generating a protonated nitric acid. What's this look like? Water, and water's a good leaving group. It leaves and you generate NO2+. We've just generated the nitronium ion that is responsible for functioning as the electrophile. So in the electrophilic aromatic substitution general mechanism, the benzene ring attacks what atom? What atom gets attacked? The nitrogen. That's how we can make a carbon-nitrogen bond, right? And so that reaction then occurs through the typical general EAS mechanism that we've already talked about. Sulfonation, the mechanism's quite easy here for generating the SO3H+. These oxygens function as a Lewis base and get protonated by the sulfuric acid, and you generate a sulfur cation. Pretty simple. Okay? What atom gets attacked by benzene in the sulfonation reaction? It's the sulfur atom. Okay? We can simply attack that sulfur atom and get our product. Okay? I am holding you responsible for knowing the mechanism of how all these electrophiles get generated. Okay? The next exam will cover this material. I did not hold you responsible for that on exam 1. But exam 2, you have to know how all of these electrophiles get generated. Okay? Because it's important. Okay? You need to know them. As you can imagine, we can also use carbocations to do electrophilic aromatic substitution. These things are called Friedel-Crafts reactions. And when the R group happens to be an alkyl group, we call this Friedel-Crafts alkylation. So here's an example where we have chloroethane and aluminum trichloride reacting to give ethylbenzene. How does that mechanism work to generate the electrophile? Kind of the same as the bromine, right? So let's think about this. We've got an ethyl group. We've got a chlorine. The chlorine has what around it? Lone pairs of electrons. I have aluminum trichloride, which is what? It's a Lewis base. If you look where aluminum sits in the periodic table, it's right under boron. Aluminum has a vacant p orbital, meaning that it can accept a pair of electrons. Where's it going to get those electrons from? It's going to get it from the chlorine. Now, this bond becomes extremely weak, right? But in this case, does this really happen? Why not? Because it's a primary carbocation. We don't generate primary carbocations even in these reactions. However, you can generate carbocations, real carbocations, by reaction of alkyl halides with aluminum trichloride if they are secondary or tertiary alkyl halides. Okay, so for example, the bottom one, right? The tert-butyl chloride reacting with aluminum trichloride, it will actually generate T-butyl cation. It's detectable. Here we just have this and our aromatic ring attacks it like that. We can't generate a primary carbocation, okay? Pretty simple to generate that electrophile. Okay? The electrophile for the Friedel-Crafts acylation, a little different. So we have our acid chloride. Aluminum trichloride. What happens? Tell me. Okay. Now what happens? This is where it gets a little different. What can happen?
Remove some electrons from the oxygen.
And how? Where do I move them to?
To the double bond. And then push the
Yep. And I get what's called an acylium ion. Notice it's got a positively charged oxygen. We do not generate a carbocation on an sp2 hybridized carbon like that, right? That can't just leave. That oxygen being positively charged, though, means that this carbon has a lot of what character to it? Carbocation character, right? And so it is actually the electrophilic atom. The aromatic ring attacks this carbon, and you generate this. But you generate an acylium ion. The formal charge is on oxygen, not carbon, and therefore we will not see any rearrangements of carbocations in the Friedel-Crafts acylation reaction. The Friedel-Crafts alkylation reaction, however, is a different story. If you have a secondary alkyl halide and you react it with aluminum trichloride, it will generate a secondary carbocation which can rearrange to a more stable carbocation. Technically, anything that can generate a carbocation, we can do a Friedel-Crafts reaction, even though the Friedel-Crafts reaction is theoretically between alkyl halides and acid chlorides and aluminum trichloride. But what other ways do we know of generating carbocations? What other functional groups can we convert into carbocations? What other reactions have we done where a carbocation has been generated? Pardon? You can protonate an alcohol. So if we take an alcohol, put it in a strong acid, water can leave and generate a carbocation. Guess what? You can do Friedel-Crafts chemistry with alcohols. Take tert-butanol instead of tert-butyl chloride, sulfuric acid, and an aromatic ring, you'll make tert-butyl benzene all day long. So through the protonation of alcohols, what else can we do? What other functional groups have we generated carbocations from? Okay, so when we're taking what and water? An alkene, right? So you can take an alkene, you can protonate that alkene, and you can generate a carbocation. So guess what? We can do Friedel-Crafts alkylation chemistry with alkenes as the electrophile. We just have to have a strong acid around. Anything that you can do to generate a carbocation can be used in a Friedel-Crafts alkylation reaction. Okay? The only thing that you can't do is you can't take chlorines or halogens that are on sp2 hybridized carbons. So in other words, if I take vinyl halide, or vinyl chloride in this case, I'm not going to get a vinyl carbocation. It won't work. I can't take chlorobenzene and generate a aromatic cation. It doesn't work. It has to be an sp3 hybridized halogen, okay, for this to work, okay, because you have to go from sp3 to sp2, and here it's already sp2. You're not going to generate these so-called vinyl type carbocations, okay? These just do not react, okay? So let's look at some examples. So here we have an example of a secondary alkyl halide. How would we name this molecule? Let's think a little bit about naming. What's the parent? It's a butane parent, right? What are the substituents? A methyl group and a chloro. So how are we going to name? How are we going to name it? 2-chloro, 3-methyl butane, right? Yep, that works for me. Notice the carbon in red. Aluminum trichloride is going to remove the chlorine and generate a secondary carbocation. You might predict that the aromatic ring simply attacks the secondary carbocation and makes the carbon-carbon bond between the aromatic ring and the red carbon. Notice the red carbon is not the one bound to the aromatic ring. Why is that? What has happened? What has shifted? So we have this, right? What shifts? One of the methyl groups or the hydrogen? The hydrogen, right? And so you end up with that as your carbocation that undergoes the Friedel-Crafts alkylation reaction, right? So what can we shift? We can shift hydrogens as hydrides. What else can we shift? We can shift alkyl groups, methyl groups, propyl, whatever, right? What else can we do? We can do ring expansions. Remember that? So if we had a strong or a strained ring, it could actually expand and form a more stable carbocation. So you can actually have this kind of reaction occur where you have a strained ring, you generate a carbocation, it expands to a bigger ring, and then it gets trapped by the aromatic ring to form the carbon-carbon bond in the Friedel-Crafts reaction. Now, interestingly enough, these primary halides also show rearrangement. How is that possible? Let's see, that's just putting one extra carbon up here. So let's see what we can do. We'll put another carbon there. Put another carbon there. I thought I showed you in the previous example that the aromatic ring simply attacked that carbon. Why is it different now? Why does it undergo a rearrangement? And why didn't it before? This takes on substantial positive character. It's not a true carbocation. But what happens is this shift can occur and generate the secondary carbocation. Okay? It can happen. Why did that not happen with the ethyl group? It can't, right? It can't do it. Here it can, right? Because you have the extra alkyl substituent on the chain. Okay? So anytime you have primary alkyl halides or secondary alkyl halides in a Friedel-Crafts reaction, what do you need to do? You need to be ready to do some rearrangements, right? You're going to do rearrangements. If you have primary or secondary alcohols and a strong acid to generate carbocations, you need to be concerned about rearrangements. If you have alkenes that have substituents around them that can rearrange, you need to be concerned about rearrangements. I told you all that rearrangements would be the bane of this course, and it's true. They're not going away. Every chapter from here on out in the chemistry, we will talk about some type of rearrangement as a possibility, okay? So you got to keep rearrangements in mind. Anytime we generate carbocations, you got to be careful about it, okay? So here's an example of using an alkene. How would we name this alkene? Hexene? Cyclohexene, right? Cyclohexene reacting with the strong acid sulfuric acid generates a carbocation. It's secondary. It's okay. Will it rearrange to a more stable carbocation? Everything it rearranges to is secondary, right? So it's like it never rearranges. So we can generate a secondary carbocation. We can actually generate an electrophilic aromatic substitution reaction with this carbocation if we do this in the presence of something like benzene. So we could literally take a mixture of cyclohexene and benzene, stir them at low temperature and drip in some sulfuric acid and get a Friedel-Crafts alkylation reaction to occur. What would the product be? How would you name the product? How would you draw the product? Let's start with that. Keyshawn, what product am I going to get? If I take cyclohexene and react it with benzene in the presence of sulfuric acid. So I've got benzene. I've got cyclohexene. I put in some sulfuric acid. What is my product going to be? I'm going to have two rings. How are they connected?
Probably with double bond.
With a double bond? Don't think about the mechanism. I'm just asking for the product. How are they connected? By a sigma bond, right? And what would the product name be? Cyclohexylbenzene works just fine with me. Why wouldn't we name it phenylcyclohexane? I suppose you could. But typically when you have the aromatic ring, you name it as the aromatic system. So cyclohexyl benzene works really well here. We can do the same thing with an alcohol. So here we have our tert-butanol, sulfuric acid. We protonate the alcohol. We've seen that reaction step time after time after time, right? Water leaves, and we end up with a stable tertiary carbocation, right? If that was to react with benzene, what would the product be? Tert-butylbenzene. Absolutely. Okay. And there it is. The Friedel-Crafts chemistries have been useful for making a variety of compounds here. For some reason, I'm going to show you how to make LSD. So you start off with a relatively simple molecule. Okay, here we've got our acid chloride. We react this with aluminum trichloride. We generate what kind of anion from this? Or a cation, excuse me? He's taking a picture of how to make LSD. I like that. Pardon?
Psyllium.
We generate the acylium ion, right? That then reacts and forms this new carbon-carbon bond, which is important for making this ring of the system. And then they do a bunch of other chemistry, which we're not going to teach you about, to actually make the molecule, okay? And so it can be made in several steps. But what you're going to find over and over and over again is that pharmaceuticals, whether they be legitimate or not, are typically made using things that you learn in sophomore level organic chemistry. Why is that? because the reactions that you all are learning are typically well-behaved, high-yielding, and pretty much so idiot-proof. I mean, and that's kind of important, right? I'm not going to teach you the stuff at a sophomore level that has 10 different pathways it can take. And you got to be really, really specific about the conditions, right? That's graduate level stuff. Well, if you're a pharmaceutical industry, do you want to deal with stuff that's more complicated or stuff that's more simple? Simple. Simple's always better, right? And it leads to greater profits. And so you're going to find that a lot of the drugs that you all take, hopefully all of them are legitimate, are made using simple reactions, okay? And that's one of the things that pharmaceutical companies spend an awful lot of time with. They may build the molecule the first time using a complicated reaction, and then they spend years trying to figure out how to make that process more efficient, more simple, okay? And so Friedel-Crafts chemistry you will find in a variety of pharmaceutical syntheses, and quite frequently it's the Friedel-Crafts acylation reaction that chemists really like. We typically hate Friedel-Crafts alkylation, and we'll talk more about that later, okay? But the reason is because it's difficult to control the Friedel-Crafts alkylation reaction. All right, so I want to take a little bit of time and talk about the exam. So the exam grades have already been posted, so you've probably seen them in Canvas, I hope. There were no offset points for the exam, but the grade that you see will be a combination of the grade from the zip grade form, the grade from the points you got on the bonus question, and the points you got on that note card that you turned in. I put all that into exam 1. So that means that there were a total number of possible points of 109. Okay? So look at your grade. I was pretty pleased overall with the grade performance. I thought you all did quite well. This was your last opportunity to have a note card. So put them away. You're not going to get to use them on the next 3 exams, including the final. Okay, so we're off to a good start. Interim grades are due for me. I've got to get those turned in. Those interim grades that you get in SOAR when you go in and look at your interim grade will only be based on exam 1 and the 4 inverted lectures that we have grades for. They will not include any offset, because we don't have any offset, and they won't include any of the extra credit stuff that you did before the semester started. All that is not going to be included. Yeah. Homework will not come into your interim grade either. Okay, so I'd have to pull all that from Sapling, and I'm just not going to do it. So that's what you're